This was the case for rotating imbalance, and m0e is the unbalanced force, and m0 is the unbalanced mass, and m is the total mass. Okay, so we derived the dA, that is dimensionless amplitude, for rotating imbalance. Similarly, we consider the case for support excitation. In this case, the support is not stable, there is some excitation provided to it, and we said that that is y is equal to y sin omega t, where y is the amplitude of the amplitude of vibration of the support. All right, and we derived the governing differential equation, we solved for it, and here we considered two cases. First case, we considered the absolute amplitude, and we derived the equation for absolute amplitude, that is x by y, and here x becomes the absolute amplitude, and that was square root of 1 plus 2 zeta r whole square divided by square root of 1 minus r square whole square plus 2 zeta r whole square. And in this case, the phase lag is tan inverse of 2 zeta r upon 1 minus r square minus tan inverse of 2 zeta r. That is the phase lag between the mass m, which is moving with xt, and it is attached to a spring and mass damper system, and you have a support which is moving with y of t. All right, so this response, this is the response, that is the motion of the mass. It lags the support excitation yt by this angle. All right, that is tan inverse whatever the term is there in this. All right, so that was the case for support excitation. And we also, now instead of defining in terms of absolute amplitude, we defined it in terms of relative amplitude. And so z was x minus y, so z dot is the relative velocity and z double dot is the relative acceleration. Okay, and we substitute that and we did all the mathematical manipulations, and we got the ratio of z by y, that is the steady state. We got the expression for the steady state relative amplitude. Okay, so earlier one was the steady state absolute amplitude, and this is the steady state relative amplitude, and this reduces again to the form of r square upon square root of 1 minus r square plus 2 zeta r square. Now if you compare this equation, again phase lag for relative amplitude will be tan inverse of 2 zeta r upon 1 minus r square. Okay, now we if we compare the two solutions which I have got, first one was for the support excitation. So in support excitation, if I replace the numerator with relative amplitude, then this equation is same as the similar to the that of rotational imbalance. All right. So if, I hope you are able to make out the similarity, and this will help you to remember things easily. All right. So we had finished up till this. Now we'll continue for the next part. So you have x divided by m0e upon m is equal to z by y, and this is equal to r square divided by square root of 1 minus r square whole square plus 2 zeta r whole square. All right, so this is the equation for dimensionless amplitude. All right, now we'll see what are the features for this equation, and then we'll plot the graph. So for r is equal to 0, dimensionless amplitude is also 0. Okay, so if I plot the graph of dimensionless amplitude versus frequency ratio. All right, so all these curves will start from 0, that is origin O. All right, so it is 0 comma 0. All right, now for zeta is equal to 0, dimensionless amplitude becomes plus or minus r square upon 1 minus r square. Okay, so when r is equal to 1, dimensionless amplitude goes to infinity. Correct. So for undamped system at resonance, this dimensionless amplitude goes to infinity. All right. Then when r tends to infinity, dimensionless amplitude becomes 1. All right. So here the dimensionless amplitude tends to unity as r tends to infinity, and that you can easily do by this equation. So if I write this equation dimensional amplitude in the form, if I divide both by r square, both denominator and numerator by r square, I get okay, I get 1 upon square root of 1 upon r square minus 1 whole square plus 2 zeta by r whole square. All right, and if r tends to infinity, then this dimensionless amplitude tends to 1 unity. I hope you are making a note of all the features that I am discussing. The quiz questions will be based on these features. A lot of quiz questions will be based on the features which I am discussing. All right. If you are not clear with anything, you should ask me immediately. So continuing on. So let's discuss few more features. So just as we did maxima for magnification factor, so we'll do the maxima for DA. Okay. All right. So to do the maxima, DA is function of R, that is frequency ratio. Okay, so take a derivative of dA with respect to R and equate it to 0. And when I solve this equation, so I am not going to solve this derivative for you. When I solve this, the solution is R is equal to 1 upon square root of 1 minus 2 zeta R square. All right, so the one which was for your magnification factor is the reciprocal of this value. All right. So this corresponds to this frequency ratio correspond to peak values. All right. Or in other words, for peak values, 1 minus 2 zeta square should be greater than 0. Okay. So this term should be greater than 0, only then the square root will be a real number. Okay. So zeta should be less than root 2. All right. So you will get peaks when zeta is in this range. It is from 0 to 1 by root. Okay. As this is another feature of this curve. Now we'll plot this curve. Any questions so far? All right. Okay. So before plotting the curve, I would like to discuss few more points. If you have any questions, please ask immediately. For zeta less than 1 by root 2, r is greater than 1. All right. So if you see, whenever zeta is less than 1 by root 2, r will be always greater than 1. The r is 1 upon square root of 1 minus 2 zeta square. Okay. So this term under the root will be always less than 1. So reciprocal of that will be always so greater than 1. So this r will always be greater than 1. All right. So what happens because of that? As you increase zeta, no, not increase zeta. So what happens? The peaks are on the right hand side of resonance frequency ratio, that is 1. All right. So peaks here you will get peaks on the right hand side of the resonance. In case of magnification factor, you got the peaks on the left hand side of the resonance, because in that case the frequency ratio was reciprocal of this. All right. Now for zeta in between 0 to 1 by root 2, as zeta increases, r will increase. All right. So because of that, the peak That is the peak value. R increases for the peak value. Right? The peak value of R also increases. So as a result, the peaks will shift to the right. Right? Okay. Now when zeta becomes greater than 1 by root 2, the term under this square root sign becomes complex. Alright. As soon as that becomes complex, peaks disappear. Okay, you will not observe any peaks. And now in this case, the dimensionless amplitude curve monotonically increases. Okay, and as R tends to infinity, dA will tend to 1. All right, so this curve will become an asymptote. The dA equal to 1 line will become an asymptote to this curve. All right. All right. So if you recall the magnification factor curves, as what do you say? As R you see the curves were monotonically decreasing, not increasing. Here the curves are monotonically increasing. All right. So I hope you remember the differences. Now what we'll do, we'll plot the. So these are the all the statements summarized. Okay. Now we'll plot the curve. All right. So we'll dimensionless amplitude on y-axis and frequency ratio on x-axis, and then we'll mark a line where dA is 1 unity, because you will need this line for a reference. Alright, so draw a horizontal line where dA is 1, and also draw a vertical line where frequency ratio is 1. Alright, so where here R is 1. Alright. Now if you remember, all the curves start with from the origin. So all the curves we have to start from origin, and I will construct the first curve for zeta is equal to 0, and at R equal to 1, this goes to infinity. Right? And as R tends to infinity, dA tends to 1. All right? This is one of the features which we derived. Okay. Then I will draw again. Remember this reference line. I hope you remember this. That corresponds to zeta. All right. So I will just write this zeta is equal to 0.707. All right. So this should be your reference curve. Okay. Everything above this will have peaks. All right. Right, so this will be, this is zeta is equal to 0. So this is zeta is equal to zeta is equal to 0.25. Sudarshan Gawande, keep your mic mute. And this is zeta is equal to, if you have a question, you go ahead and ask. Zeta is equal to 0.5. So these are just sample values. So all this should be less than 0.707, and all the values which are greater than 0.707 should fall below this curve. All right, and as you can see, all the curves which are, so suppose this is zeta is equal to 2, This curve, which is has the frequency ratio in form of complex, this is monotonically increasing and there are no peaks. These ones have peaks and they are showing these peak values, and these peaks are shifting to the right. Correct? As zeta increases, the peaks will keep on shifting to the right till you reach this value of 0.707. After 0.707, these peaks will disappear and it will monotonically increases. And if you see all the curves, they tend to unity or tend to dA is equal to 1. Alright, so this is how you have to plot the graph, and these are the features of the dimensionless amplitude versus frequency ratio. Now here this dimensionless amplitude is common to both, that is rotating imbalance and what do you say, support excitation. Alright, support excitation. Alright, so rotating imbalance as well as support excitation, you get the same curve because the dimensionless amplitude, this expression is same for all, that is r square upon square root of 1 minus r square whole square plus 2 zeta r whole square. Alright, any questions so far?
Sir, then what you have written that the dimensional amplitude is monotonically increases as r tends to infinity.
Yes, see, as r, this axis tends to infinity, right? So you see this curves for zeta greater than 0.707, or that is 1 upon root 2. Right? So as r tends to infinity, these curves are now monotonically increasing. There is no peak. Here they are not monotonically increasing. There is a peak, then they decrease. Alright, so they
Okay, okay.
maximize till certain point and then. Okay. Alright, so any other questions? Okay, now this last small portion is remaining. So that is the force vibration of a due to reciprocating unbalance. Okay, so now here you have a piston moving inside of a cylinder for a IC engine, and the base is mounted on a spring of spring stiffness K and damping constant C. Alright, so this is reciprocating. So M is the total mass of the reciprocating machine. So total mass is M. Alright, M0 is the mass of this reciprocating part in kg. L is the length of the connecting rod, E is the length of the crank, and N is the obliquity ratio, that is L by E. Okay, and omega is the angular velocity of the crank. So this crank is moving with angular velocity omega. Alright, so this is the arrangement, general arrangement for IC engine, and for that inertia force Fi is equal to mx double dot. Okay, so x, now this expression for acceleration, this you have already studied in your theory of machines. I hope you recall that. Okay, so that becomes m0 omega square e into sine omega t plus sine 2 omega t divided by n, where n is the obliquity ratio. All right, and this second term, this is called as your, so this is the term corresponding to omega. So this is your first harmonic. Alright, so what do you mean the first harmonic? This corresponds to your first natural frequency. I hope you recall your first lecture where you have a, if you have a continuous system where then you have infinite number of natural frequencies. Okay, so similarly this system in reality will have infinite number of natural frequency. We consider only the first two terms when you are doing derivations in your theory of machines. Okay, the second term corresponds to second harmonic, or this term is corresponds to second natural frequency. natural frequency. Both the natural frequencies are contributing to the acceleration, but this term is very small, so generally we neglect this term. So our inertia force reduces to m0 omega square e, okay, which is similar to our expression of F is equal to f0 sine omega t. So again you get the steady state amplitude equation as x is equal to f0 by k divided by 1 minus r square divided by 2 I plus 2 zeta r whole square. Okay, so your x steady state amplitude is m0 omega square e divided by k, that is m omega n square divided by square root of 1 minus r square whole square plus 2 zeta r whole square. All right, and that is I can rearrange these terms and write it as x divided by m0 e by m is equal to r square upon square root of 1 minus r square whole square plus 2 zeta r whole square. All right. Okay. All right. So that is all. Now we'll start with the quiz. Any questions before we go to the quiz?
So even this is similar to the case 2 and case 3, you know.
Yes. All right. So start. Open your quiz and start with the third question. The third question is there on your screen. Okay. So this is a big quiz. So I will give you say 15 minutes. Okay. To complete this quiz.
Sir, not visible.
Just hold on a minute. It will be visible. Just refresh your screen. Okay. Just a minute. Just a minute. Are you able to see now? Sudarshan,
Yes, yes.
everybody is able to see? Okay, you can start with the quiz.
So
Yes,
we have to answer this quiz on lecture 22, module 3, right?
yes. Just refresh your. It is the same link as yesterday. I have just changed the name from lecture 21 to lecture 22. That's all. But the link is same. First two
Okay.
questions you have already answered, so that should be with you. So you enter the answers whatever you have got it yesterday. You can start with question number 3. You have till 11 o'clock to complete the quiz. If you have any questions other than this, you can ask. You can complete the quiz and submit it. I would suggest you take a snapshot of this page because there are more questions. Either take a snapshot on your mobile or your PC so that you can refer it. Or are done with the first 11 questions? Can I go to the next one?
No, sir.
All right.
Sir, we require more time, 2 to 3 minutes.
Okay. All right, done. Those who are done can let me know so that I can switch to the next page. Can I switch to the next page?
Sir, a couple of minutes, sir.
You can just take a snapshot of this screen. All right, those who are still remaining. How many are remaining? Raise your hand in the chat box.
So we have to submit this.
No, it is not done. There are there are more questions. When you are done with all the questions, only then you can submit it, na? Have you seen all the questions? All right. I think most of you are done. Those who are not done, take a snapshot. These are the next questions. All right. Again, all are true and false. This should not be there. Comma. If anybody has any is not clear with the wording, or you can ask. Those who are still doing this second group of questions, that is question number till 19, should raise their hand so that I can know how many students are yet to finish. You can raise the hand in your chat box. All of you are done?
Sir, we are raising hand because we are
Okay.
left to do it.
Okay, okay. Got it, got it. If you are done, you can unraise that unraise the hand so that I can know. Those who are still remaining, please take a snapshot of the question set so that I can move on to the. I will give you. Let's see. I'll give you 2 more minutes. You're already. Uh, the time is up. All right. I think I should shift to the next page now. The last page for the quiz. Okay, take a snapshot of this page so that I can continue to the next page. If you want, I will come back to it. Those are still remaining. Okay, I'm switching to the last page. Okay, these are the last 6 questions. complete this question and submit your quiz. If anybody wants to see any page, if you miss anything, you can ask. Those who are done can submit the response. Okay, I'm going to give you 2 more minutes. After that, the quiz will be closed. Start submitting your responses. Already I have given you for this has been like 15-minute quiz, but already it is more than 15 minutes. Any more time is not justified. All right. So submit your responses. All right, last minute. Submit your responses. All right, time is up. I'm closing the responses now. All right, responses are closed. All right, I will just post the score quickly. All right. So scores are posted. You can just review your quiz. In the meanwhile, I will take the attendance.
Sir, the answer for 14th one is not given.
Answer for 14th one. Let me check.
Sir, have you given the answers
14th.
out?
Yes, yes. 14th one I have not marked it. Just a minute. Which is the 14th one? All right, so you can just refresh it. It will just what do you say?
For the 15th one, what should be the answer? Is it true or is it false?
You should see. You should be able to see it in the preview, right? What do you see?
Yes, sir. I have marked true, but I didn't understand why it's false.
Which one? 15th one. 15. At resonance for a system under rotational imbalance, the dimensional amplitude goes to infinity and damping ratio is 0. True or false? So what it is?
So it should be true, right?
Ah,
So, but it's marked false as the right answer in the quiz.
Sir, but when the damping ratio is
at resonance for a system under rotational imbalance, the dimensional amplitude goes to infinity when damping ratio. Yes, it should be true. Actually, okay, I will let me correct it. Alright, you should see the updated score. You can just refresh it. Alright, so at resonance, when damping ratio is 0, it should go to infinity. Alright, so B2 batch today as practical. Any other questions, please go ahead and ask. I apologize for the error.
Hello, sir.
Yes.
Sir, please can you open the form for like 10 seconds?
No. Any other questions? Who is that?
Sir,
Yes, what is the name of the student?
Parth Mahajan.
Ah. Yes, any other questions you have? Any clarifications you can ask? Alright, so today B2 batch is practical and you're going to do the experiment on spring mass system, right? So, and in that you will need to use Excel. Okay, now if you don't have a Excel, then you have to use a graph paper. Alright, you have to construct a graph using Excel. So we will see how to do that during the practical. Any questions on the quiz before we end the session today? We are down to the last minute.
No, sir, but please upload the means Excel sheet of our results on Teams.
You should have seen. Are you not able to see the results now? When you click on the link,
I have not checked, sir.
I have already posted the response. See, you can check the link. I will upload the Excel sheet also. Yes, any other questions before I end the lecture? All right, so during the practical B2 batch, you should have your Excel ready on your computer. We will be doing some plotting of graphs and so many things you have to do. So today we will be doing the experiment on spring mass system. Okay, natural frequency of a spring mass system with a helical spring. Okay, so that's all for today. Thank you. All right, so you can leave if you are done.